the BI-CMDB. In this section we present, in an exhaustively manner, our view and proposition for building a CMDB adapted to decisional systems, which we consequently call the BI-CMDB. In order to understand how this is built, we present a schema of the data flow in the organization of 5 modules that are part of our approach. The SB2 BI-CMDB simplified schema. On the bottom level we have the data source that provide the monitored data. As mentioned, these are distributed, non-centralized and under different formats. Next, there is a data collector module, which gathers and archives the data sources. This is the first level of centralization while greatly reducing the size of this data by archiving. Following, an operational CMDB build with the data collector centralized information. It is the first level of filtering, parsing and interpretation, of the monitored data, which allows to keep only the interesting data for further analysis. Analysis of the OCMDB is brought climbing up to the analytical CMDB, which builds a data warehouse architecture, by specific objective data marts, with the data from the OCMDB. We note that the elements of the OCMDB and of the ACMDB correspond to IDLE's guidelines, with the addition of elements that correspond to the specifics of DSS. Once the ACMDB has been constructed, 2 more levels of information access, by user, are added, with a module for publishing the reports built on the ACMDB data warehouse and a web portal for consulting these reports and for dynamically exploring the data from the CMDBs. These last 2 are not of interest for this lecture, but equally make a challenge, from the study of computer-human interaction and GUI design. A detailed description of the first 3 modules that are interesting to the BI-CMDB is done in the following. Examples for each of them are provided, in the light of the differences with the traditional CMDB and on the characteristics of DSS. The data collector is the first module in the data flow towards the construction of the BI-CMDB. Its main objective is to gather and archive the various interesting monitoring information. The core of the data collector architecture is the connector. A connector represents a generic interface for defining the elements that allow the gathering of information from a data source and the methods used for this process. The parameters of a connector allow him to connect to a target machine, i.e. name of the machine, connection port, data source location and type etc., recover and archive the data from the sources and send these archives via FTP connections to the machine which is in charge of archive analysis and construction of the OCMDB. Depending on the target machine installed by software solution, various implementations of the generic connector are required, for example an Oracle Hyperion SOBS connector or a BO connector. As we have seen previously in the monitoring section, there are 3 types of data sources: logging files, logging databases and specific console commands. A connector can specify any, or all, of these types. Following the IDLE guidelines, a separation of the data fluxes is done for each connector, where possible. There are 5 types of data fluxes: I, logging, log, 2, exception, XCP, 3, parameters, param, 4, performance, perf, and v, errors, This separation persists further on with the construction of both the CDMB and the ACMDB. Another argument for this split is the fact that some solutions use different data sources for different fluxes. For instance, with Essbase, the monitored information is usually stored in plain text files, .log and .xcp. These files allow the identification of all the required data with the exception of the configuration parameters. Due to the fact that they change rarely, their identification through log files is very difficult or even impossible. This is why for this task, specific console commands are used for the paramflux. Example. We show below an example of data collection for a connector implementation for the Oracle Hyperion Essbase server, with the various connector data fluxes. The Essbase server log files are under the /log repository of the Essbase installation. The connector will specify the machine and port, for connection to the Essbase server, and the place of the Essbase installation, for example c:/Hyperion/logs/Essbase. This repository contains a suite of .log and .x files, that are organized by application. Here the term application indicates the regrouping several data marts which suit the same business objective. The .log file contains various information about the application and its data marts, which is interesting for the log, perf and data fluxes. An extract of the file is shown below for a data retrieval operation on a data mart from the application. Local/budget application/info 1,013,210 user set active on database. Local/budget application/boom/admin/info 1,013,164 received command from user. Local/budget application/boom/admin/info 1,001,065 regular extractor elapsed time, seconds. These lines permit to identify that there was an Essbase report request, data retrieval, on the Boom Data Mart, part of the budget application on 31st of January at 17:57 and 51 seconds from the admin user, which lasted 29.64 seconds. These elements represent the interesting monitored information, and are recovered from the last 4 lines. The first 2 lines are useless. This filtering process is done at the construction of the CMDB. The .x file contains the information needed for the data flux, logging the fatal crashes of the Essbase server. An extract of this file could be: current date and time, Friday, September 19, 11:29 and 1 second 2008. Application name, budget, application. Exception log file, /app/hip/hyperion/analytic, services/app/budget, application/log 00001.xcp. Current thread id, 2. Signal number, 0/15 equals termination by kill. Last, in order to get the configuration parameters of the application data marts, the scmd command line console is used, i.e. getbinfo, getupinfo etc. The results of these commands are written into customized text files, which assure the perf data flux. The role of the example was to show that the monitored information is very different, and data sources and formats vary even within the same implementation. The data collector has the role of assuring a first centralized level of information, with no data analysis intelligence. The only intelligence in the module allows an incremental data collection, such that data is not redundant. For example, if data is monitored once each day, each collection takes only the information from the logs corresponding to the last past day. The following levels of information centralization are shown next with the construction of the CMDB and the CMDB.